next talk is by DJ of Deepmind, Verifying Learners.
Thanks, Stephen, and thanks to the organizers. Is the mic working? Can everyone hear me? Okay, cool. So this is joint work with several of my colleagues at Deepmind. Essentially, it doesn't directly overlap with the theme of the workshop, but I think it has implications. So the work is really about taking all these complex machine learning models that we're building using deep learning algorithms and trying to make sure that they satisfy desirable properties that we would like them to satisfy given the domains that we're applying them in. And if you imagine the predictions of these algorithms being part of real-time decision-making systems, it's important that you have a priori checks on that give you guarantees that they will be doing the right things under all circumstances. So that's really what this work is about. So many of you might have heard about the recent fatalities, unfortunate, with the Tesla self-driving cars and the Uber ones. Essentially, what this kind of drives towards is the need to have much stronger safety checks on the systems we build using data-driven AI technologies. And to really understand the core of where these vulnerabilities come from, I'm going to start my talk by looking at what machine learning actually means, and kind of, making some arguments that show that the way machine learning is done right now, it's almost inevitable that you would see things like this happening, and how we can go from the way things are done right now to a better way of doing things that hopefully will reduce the chances of things like this happening, right? So our motivation is to really have ways to check our machine learning systems. And so let's think about the motivation for machine learning, right? So you can think of machine learning as a paradigm for implementing certain tasks on a computer. But let's first think about how we would specify tasks. So let's start with something very simple, like you want to write a function to sort a list. This is a specification in an informal language. It's a natural language. You could turn that into a formal specification using a logical formula or in any kind of formal language. And what we do in machine learning is typically to replace this complete specification by just input-output examples, right? So we're going to say that rather than defining you this formula that tells me what the right thing is to do in all possible situations, I'm just going to give you pairs of inputs and outputs that tell me for those specific inputs what the right output should be, right? So, of course, the problem with the first type of specification is that it's ambiguous. There may not be a very precise way to translate that into computer code. A complete specification in many tasks is very time consuming, and if you think about tasks like computer vision, it's almost impossible. But as we know, the partial specifications, especially in high dimensional spaces, if I just give you a small set of inputs and outputs, this is a very incomplete specification of the task at hand, right? So the question is there a middle ground between these that somehow combines the best of both worlds? And that's really what we want to drive towards. So what do we do in supervised learning, right? So we have a bunch of inputs and outputs. In this example, you have images of cats and dogs, and you want to learn a classifier that, given the image, is going to predict whether it's a cat or a dog, right? And so essentially, your learning algorithm is going to learn some kind of mapping from X to Y that, given any image, will either predict whether it's a cat or a dog, right? Of course, if you look at the space of images, it's a very high dimensional space. And even if you have millions of data points, it covers a very small fraction of the space of all images. So in some sense, trying to learn a complete classifier between cats and dogs just based on 1 million examples of cats and dogs, it's a very underspecified task, right? So this is really what supervised learning is doing. Given a specification in terms of input-output examples, you apply some machine learning algorithm and you get an implementation which is a predictor that, given any new input, will predict the label for that. Of course, we have, if you've been following the news, there's so many examples in recent years of this kind of approach failing. There's these examples of people with dark skin being labeled as gorillas in Google Photos. There's a case of self-driving cars crashing. And then work done here at Berkeley has shown that you can do these very mild stickers on top of stop signs and cause neural networks that do vision on those to hallucinate all kinds of crazy things. You can have machine learning systems interacting with humans and humans kind of behaving adversarially. So there was this chatbot that Microsoft released that after 24 hours became a Hitler loving sex robot. And they had to actually take it down. OpenAI built this really cool algorithm that does plays this game of Dota, but again, like within hours of them releasing the code, people were able to find situations where the algorithm did very strange things. There's also this increasing issue of algorithmic bias and fairness, where essentially you're using these machine learning algorithms to make decisions that influence people, and the algorithms are trained on data which comes from potentially biased systems, and naturally the models that you learn are going to inherit these biases. And so essentially you want to really have ways to check what kinds of biases your algorithms might be learning, and somehow guard yourself against these. Right? So really what this is all getting to is that we need much richer specifications if we really want machine learning algorithms to work in the wild. A few examples are listed on this slide. You would want some kind of robustness to adversarial perturbations of the inputs to your models. For some notion of fairness or unbiasedness, which themselves are very tricky to define, but let's say you come up with some reasonable definition. We want ways to check that our machine learning models are fair and unbiased, and we want ways to train our models to be fair and unbiased. If you're applying machine learning in some physical domain, maybe you want to make sure that the models of physics that your machine learning models are learning are physics compliant. For example, they should satisfy conservation of energy or momentum or any kind of physical principles you might want, right? So in today's talk, I'm going to mostly focus on the first kind of specification, which is robustness to adversarial examples. But I'm happy to talk about any of the others. We're actively looking into all these areas. Okay, so essentially we want to build towards this vision of a specification-driven AI, where we're combining verification techniques from the formal methods community, the convex optimization community, to actually check properties of machine learning models with the more traditional approach of specifications based on input-output examples, but also augmented with this robustness to adversarial perturbations, which is essentially going to be checked by our verification procedure, in combination with adapted learning algorithms to essentially get a verified implementation of our machine learning model, right? So you want to learn a classifier as well as some kind of proof that the classifier satisfies your specification, right? Okay, so let's talk about how you might go about doing this and why this is hard in general and how you get around the hardness, right? So essentially, we want to look at the ways in which machine learning models are tested as of now. Typically, they're tested statistically. So let's say that you're learning some kind of neural network, which is just a layer-wise mapping between inputs and outputs. Given some input, is going to predict some label. And your statistical test is that when you're training the algorithm, you hold out some data that you don't show the algorithm. And based on this test data, you test whether for a large enough fraction of the data that the algorithm has not seen in the past, it's able to classify those examples correctly, right? So this is a statistical test. And if your model passes the statistical test by predicting correctly on a large enough subset of the test data, you accept it as being a fine model. You can make this test slightly harder by saying that there may be an adversary that corrupts your test input by a small amount before asking you to predict. And so then the question is, if I have a clever enough adversary, can I still make correct predictions? This is something that's known as adversarial testing. Of course, both of these are still not assuring you that your models satisfy the specification, because this test is only as good as the adversary that you come up with, right? So if I could come up with a better adversary, I could still break the model. So the question is either of these tests sufficiently secure, and what would happen if there is a stronger adversary? So at NIPS, which is one of the machine learning conferences, there was this competition last year on trying to build defenses against these kinds of adversarial attacks. And there's a variety of techniques that were proposed that both came from papers published in the literature, but also just submissions to this contest. And at Deepmind, we did some work along with, in parallel to work that was done outside of Deepmind as well, that showed that actually, I'm sorry, so this was just, the red line should not, it applies to all of these models, is that essentially, if you design your defenses to be robust against a specific adversary, you can often find a stronger adversary that actually drives the robustness all the way down to 0. So even though there were all these models that were actually claiming to be robust to adversaries, it was because they were potentially using rather weak adversaries. So if you actually use strong enough adversaries and enough compute, you could actually break all of these models. So this really calls for the need for worst case guarantees, which is what we call verification. And you can think of verification at various levels. The model level, what we call module level verification, is just about verifying input-output properties of single neural networks. So think about a neural network that's classifying handwritten digits. So given that image of a 7, it's going to predict 7. But we want to augment this with, say, this network with the specification that says that I want to continue to predict 7 for all images of this type. So I'm going to take my original image, and I'm going to add a small amount of noise to it. And as long as that noise is small enough that says that perceptually it should not change the nature of the image, I want to continue to predict 7, right? So my specification is that for all my input data, as long as I add small enough noise to it of any bounded magnitude, I continue to make the same predictions. Right? Okay. You can think about this also at a system level where your neural network is not being used just to make predictions, but it's being used as part of a larger system. And so, just to consider like a very toy example of this, maybe you want to take pairs of digits and predict the sum of those digits. And then in this case, your specification would be to say that you still continue to predict the correct sum, irrespective of taking any pair of images and adding bounded noise to that pair of images. Right? Clear so far? Okay. So of course, this would be great if we could do it, and people would already be doing it if it was very easy. The problem is that verification in general is a very difficult problem. The most obvious way to do it is to do it by enumeration. So you could imagine discretizing the space of all perturbations of your image, and if you count the number of such perturbations, then it grows exponentially in the size of the input, in this case the number of pixels of your image. And you're just going to check manually for each option in this enumerated space of perturbations whether your model satisfies the specification, and if it passes this very exhaustive test, then you're going to declare it to be safe, right? So if you actually compute the amount of time it takes to actually do this computation, even for a very small data set, which is this MNIST data set of handwritten digits, even if I allow each pixel to be perturbed by 1 unit or 2 units up or down, I quickly reach a crazy number of possibilities. And if you're familiar with the AlphaGo program, even the AlphaGo program was actually only reasoning about something that was about a 1 unit perturbation in this space. So this is a hard problem in general. It's NP hard, you can show even for single hidden layer neural networks. So as long as soon as you have even a single hidden layer, so you have a 2-layer network with a single hidden layer, it already becomes NP hard, right? Okay. So we're going to see how we get around this, but before that, let's see what verification could do for us based on the algorithms that we have developed. So we're going to again look at this MNIST classification problem, and we're going to look at the space of epsilon perturbations of all our training data or test data. And we want to ask the question, out of all of our test examples, how many of the test examples don't have an adversarial perturbation within a radius of size epsilon, right? So for how many of my test examples can I guarantee that no matter what perturbation I do, as long as it's within this radius of size epsilon, I cannot change the classifier's output, right? And so this is what we're able to do with our current algorithms. So the black line, the dark line, is an upper bound computed by our verification procedure that says that no matter what adversary you had, as a function of the size of the perturbation, I could not increase the error rate on the test set by more than the amount indicated by the solid line. The dashed line is a lower bound that comes from a specific attack algorithm, right? So this is basically, I design a specific kind of adversary that tries to attack the model, and it's able to increase the error rate up to a certain point. So you can see that as the perturbation size grows, the gap between the upper and lower bound grows, but it's still kind of at a perturbation of size 30, which is roughly 10% of the grayscale on this problem. We still have reasonably tight bounds. Okay, so how does what we do compare to prior work? I'm going to compare it in terms of 4 of these axes. We're going to look at completeness, which is the property that our verification method is exhaustive, right? So either it's going to find a proof of correctness that our model satisfies the specification, or it's going to find a counterexample that shows that our model does not satisfy the specification. Complexity is computational complexity. Integration with learning basically means that we want to do this verification, but ultimately we want to feed the results of the verification back into the learning algorithm so that we can learn models that satisfy the specification that we want. So is it easy to integrate this verification algorithm with the learning? That's another consideration. And a lot of the verification algorithms that were proposed in literature before only work with piecewise linear neural networks. So they don't handle things like sigmoids or tangents, which are transfer functions that are used quite commonly in neural networks. And so that's this is about how general a model the verification method can handle. So the first 3 first 3 rows here are algorithms that came out of the formal verification community. So it's work done by people who work on SMT and SAT solvers and model checking and that kind of stuff. And typically these algorithms, they focus on completeness, but they're somewhat questionable on complexity in the sense that there could be instances of the problem where they take very long to complete the verification. This algorithm here as well also uses integer programming and potentially is susceptible to that. This year there were a bunch of interesting algorithms that came out from the machine learning community that sacrifice on the completeness, but improve significantly upon in terms of the complexity of the algorithm. And they also integrate well with learning algorithms. So they were designed to be verification procedures that can be folded into learning algorithms. On the other hand, this approach does not handle piecewise, non-piecewise linear neural networks, and this algorithm only applies to single hidden layer neural networks. So our approach in some sense generalizes to all possible models. It can integrate with learning algorithms, and it is of very acceptable complexity, and I'll actually show you some numbers that verify this. Right. So note that on this slide I'm not talking about a lot of the other work that has been done on trying to promote robustness to specific kinds of attacks. This is only algorithms that actually do provable verification of neural networks. Okay, so let's think about how we might go about doing this verification in a tractable way. So let's look at this very simple neural network which has 4 inputs, and it receives inputs with some perturbation radius of 0.01. So these 2 inputs are nominally 0.1 and they can be perturbed by up to 0.01. These inputs are 0.1 and minus 0.1 again can be perturbed by up to 0.01. They pass through a weight of a unit weight. So they're just mapped as identity, and then they pass through this ReLU nonlinearity. For those of you who don't know what the ReLU is, it's just this piecewise linear function, right? So essentially it's equal to 0 if x is less than 0, and it's equal to x if x is positive. Right. Okay. So if you reason about how what the numerical range of the output would be, you can show that the score for this label of 0 would be between 0.2 plus or minus 0.02. Here it would be between 0.01 plus or minus 0.01. And so just by doing this simple propagation of bounds from the inputs to the outputs, you can reason that the score for label 0 would always be larger than the score for label 1, no matter what the inputs are within this perturbation. Right? Does that make sense to everyone? I'm just kind of propagating the bounds and the inputs through the nonlinearities in this model. Yeah.
Just to check, and maybe for other thresholding functions, there are going to be no numerical questions here.
There are going to be what?
Are there going to be numerical questions? Finite representations?
Oh, you mean like finite precision type questions? Yes, of course, yeah. And you know, here I picked all unit weights, but in general your neural networks could be, yeah. So if you really wanted to do this rigorously, you would have to do exact precision arithmetic and stuff, kind of like really computing rigorous outer bounds on all of your floating point operations. In our view, doing that is going to add a lot of overhead, and so far we haven't seen evidence that actually worrying about the floating point errors makes things much worse. And actually some of the papers from the fault verification community have actually checked this by using SMT solvers with exact precision arithmetic and comparing it with floating point arithmetic, and they found that at least in many of these problems practically it doesn't make too much of a difference. But I agree with you that to actually get a formal proof you will have to reason about the errors introduced in the floating point.
Not checking may leave an exploitation open.
Okay, yes. But again, like empirically, it does not seem to be the case. So if you do the verification with floating point or with exact arithmetic, it doesn't seem to matter in many of the cases. Other questions? Okay. So essentially, this is the key idea that we're going to use, and we're going to scale up and tighten these bounds using ideas from duality and convex optimization, which I will explain in the next few slides. How am I on time?
15 minutes?
15? Okay, cool. Okay, so essentially we're going to pose verification as an optimization problem. To do that, I'm going to introduce some notation. So this NN applied to X and I refers to the confidence that the neural network believes that input X should receive label I. So this is the score for label I given to input X. And I'm going to call I of X the true label, so the correct label corresponding to the input X. So if this was an image of a cat, this is going to be the label that says cat. And I'm going to look at the difference between the score that the neural network gives to any other incorrect label J as compared to the true label. And essentially the adversary is going to try to maximize this difference, right? So the adversary is going to try to boost the score for some incorrect label relative to the correct label. And so I can pose the adversary's optimization problem as follows. He's going to try to boost the neural network score for the input for some incorrect label relative to the correct label over all inputs within some epsilon perturbation of the nominal input, right? Okay. So the point is that this optimization problem by itself could be very difficult, but I don't need to compute the exact value of this optimum. As long as I can bound it above by 0, essentially I have a proof that the adversary cannot attack my model, right? So this allows us to essentially somehow relax this optimization problem that will allow us to get upper bounds on the maximum value. And if that relaxation itself produces a bound that's smaller than 0, then essentially we're done, right? That's the key idea. So in order to set up the relaxation, you can think of the computation being done in a neural network as a set of constraints. So what's happening in a neural network? So you receive some input, you apply some simple transformation to it, which is apply some kind of affine mapping and then pass it through something like this. Then you get the activations at the next layer of the neural network. And then you're going to apply another such transformation and then keep going until you get the outputs, right? So it's just a cascaded application of very simple transformations of your input. And we're going to denote by NN of X the set of scores for each of the possible labels that the neural network can produce. So if I try to write down the adversarial optimization problem in terms of this picture, so I want to maximize some linear function of the set of scores that my neural network produces for all possible labels. In this case, the C is just going to be a +1 -1 corresponding to the incorrect and the correct label, subject to the constraint that at each layer, the layer L is going to be some transformation applied to the activations at layer L -1, right? And then I have that the activations at layer 0 are equal to the perturbed input, and the perturbed input is within epsilon of the nominal input, right? So essentially, this is really the constraint that's difficult in terms of optimization. It's a nonlinear equality constraint. And so I'm going to do the most natural thing. I'm going to do a Lagrangian relaxation of that. I'm going to have a Lagrange multiplier that takes that constraint and relaxes it. And essentially, by weak duality, I know that for any choice of lambda, this is going to give me an upper bound on the worst case adversarial perturbation. And so essentially, as long as I can find you a lambda such that this maximum is smaller than 0, I have a proof that my model is safe, right? So this is exactly what we're doing. So of course, this is a relaxation, and in general, the bounds could be quite loose. We're solving NP-hard problems. We were able to analyze some special cases to actually give some further guarantees on being able to compute tight bounds. In order to do this, we have to make some assumptions. So we have to assume that the perturbations are constrained in the 2 norm, and we also make this very strong assumption that we only have 2 layers in the network. So essentially, we have our input, a single hidden layer, and the output layer. Under these assumptions, we can prove the following. So there is a constant kappa that's a function of the parameters of the neural network, such that if your perturbation radius is smaller than kappa, we can actually solve the verification problem exactly using a projected gradient style algorithm. So you can actually compute the worst case adversarial attack precisely using a simple projected gradient algorithm. And if epsilon is larger than that, we can still obtain an additive approximation of the worst case adversarial perturbation, where the approximation grows as epsilon cubed times some factor that depends on the parameters of the neural network. Okay, so I just kind of want to reemphasize the advantage of viewing verification in this way. First of all, we can handle general networks and architectures. It applies to basically every kind of feed-forward neural network you might encounter in practice. It's an anytime algorithm in the sense that as long as I can produce any value of lambdas for you, I have a valid bound on the adversarial objective. So if I have a computational budget on the verification, I can stop at any time, take the values of lambda that I have, and essentially output the bound that I get from that. It can handle fairly general specifications in terms of constraints on the inputs and outputs of the model. And based on the results I presented on the previous slide, we have special cases where we can actually obtain exact or approximation guarantees. And the final nice thing about this is that because we go through this dual approach, we can essentially integrate this very easily with learning, because we can essentially replace the training objective for the neural network with the dual function. And essentially, by doing that, you're actually minimizing this upper bound on the adversarial effect on your model. So this is some results that we got. Again, counting the number of test examples for this image classification problem that don't have an adversarial example within a radius of size epsilon. So these curves up here are from a previous approach that came out earlier this year, which basically mostly computes vacuous bounds. It's not able to. So essentially, at a 0 perturbation of all the approaches give you a non-trivial bound, which is trivial. But then as soon as you have a small perturbation, these previous bounds got pretty bad. The dashed lines are again the lower bounds on the adversarial accuracy that we get from the specific attack that we design. And the the solid lines are the verified bounds that we have. So the different colors just correspond to the 5 different neural networks that we trained for this task. You can apply this to more complicated specifications. So we looked at this problem where you take a GitHub repository and, sorry, your question? Yes.
So this graph on the previous slide, so this is for the L infinity norm?
Yes, this is on the L infinity norm, yes. We looked at GitHub repositories, and we looked at commits to these GitHub repositories over time. And our goal is to predict whether the repository will reach a certain number of commits at the end of 2 months. So you can think of this as some kind of evolving prediction problem where, based on evolving features like the number of commits so far or the number of committers so far, I want to make an estimate of whether I will reach a certain number of commits. In this kind of problem, it's desirable that your classifier doesn't keep switching between yes and no, right? So you don't want a classifier that says that yes, I will reach a certain number of commits, and then suddenly switches to no, and then switches to yes again. So this kind of phenomenon is undesirable, right? So you say yes for some time, then you say no, then you say yes, then you say no again. You don't want this to happen. And so you want some bound on the number of times your classifier actually makes this switch between yes and no. And based on our verification approach, we can actually get bounds on that as well. The green is a verified upper bound on up to, so if you look at day 60, this number means the fraction of days on which the classifier switches prediction from yes to no up to this day, right? And the red is basically an attack that tries to maximize the number of switches. And so this shows that you can actually get very tight verification bounds. The reason the curves are fuzzy is that this is averaged over a large number of repositories. You can also do other kinds of tasks like the one that I mentioned, where you want to predict a sum of digits and you want to make sure that you continue to predict the correct sum in spite of perturbations. I'll skip over those results because I really want to kind of talk about this idea of learning verifiers for a few minutes, if I have that. Is that okay? Okay, cool. So essentially, we want to fold the verification into the learning process. And in order to make this computationally tractable, what we figured is that we can actually use another neural network to do the verification itself. So we can get a neural network that, given the input image, actually predicts these dual variables that we do the verification with. And once we have the dual variables, you can actually get a bound on the adversarial error rate. And you can simultaneously train these two neural networks, the predictor and this verifier, together. And this gives us a much more tractable approach than all the previous algorithms. And so you have this kind of verified learning approach where you have your training algorithm and you have your verification algorithm, and both of them are feeding off of each other, trying to learn as robust a model as possible. And so with this approach, we are able to, so let's ignore the blue and the green points. These two are the points to focus on. This was the previous state-of-the-art verified model based on this paper that came out earlier this year. We used exactly the same neural network architecture, and we are able to get a better adversarial bound with a better nominal performance. So we are able to improve on both dimensions, and we are also able to improve on the training time. So this approach took about 5 hours to train this model. On comparable hardware, we take just about 20 minutes. And the main idea that gives us those savings is this idea of using a neural network to do the verification itself, that amortizes the cost over all the test examples. So I think I kind of touched upon a lot of issues. I think as a theory audience, I think there's a lot of interesting questions for you guys in this space. Of course, there's this issue of when can verification be done tractably. We had some results for single hidden layer networks. Can we extend this beyond? There's also this issue of theoretical foundations, right? So essentially, when we did this idea of integrating the verification into the learning algorithm, what we found is that by doing this, we actually learn models that are easy to verify. So if you just train some model based on some agnostic approach and then try to verify it, it tends to be much harder to verify than if you feed the verification back into the learning. So is there some kind of theoretical basis we can give for this phenomenon? I think that would be really interesting. At Deepmind, we have a lot of expertise in reinforcement learning, and you can imagine doing more sophisticated types of verification that actually require some kind of combinatorial search within the verification process. And a lot of these verification problems have common structure. And so the question is, can you use reinforcement learning to guide the process of verification? And finally, there's this interesting question of fundamental trade-offs, which I think a lot of people in controls worry about, is is there a fundamental trade-off between nominal and robust performance of the model? What is the Pareto frontier of possibilities that I can achieve? If you start to add more and more specifications, can I compute these multidimensional Pareto frontiers? I think that's a very interesting question to look at. Also, I wanted to mention that we are hiring, especially in this space at the intersection of formal methods, controls, and learning. So if you're interested, come and talk to me. You can come and work in one of these cool offices. And I'll leave you with this picture, and yeah, that's it. Thank you. Yeah.
You started out giving this example of the Uber fatality. Mm-hmm. I couldn't connect that to your end slide of epsilon's verification. I just don't see what's the connection.
Right. So we're a ways away from being able to verify something like a self-driving car.
I don't know why what that would mean. Can you explain that? 'Cause I understand there's no epsilons over there.
Right.
I understood that. But I don't understand what verification would mean in that particular context. Is it
So the idea would be that given some kind of formal model of the environment in which the car is operating, can you verify that it would satisfy some property like never getting close enough to some obstacle?
the formal model of an environment for that Uber car look like?
Yeah, this is something that requires thought. I haven't.
Sorry.
Yeah.
The connection seems to me extremely tenuous. I can understand the 7 business,
Uh-huh.
taking some pixels.
Right.
And the Gen 7 plus 0 is 7, but I don't understand the first claim, the first slide.
Uh-huh.
The rest
This
is
is the vision.
Pardon me?
I think this is the vision, right?
Right. So, no. So, okay. So, what I would argue to you is that if you, let's say that there was some way to come up with a formal model of the environment in which the self-driving car was operating, right? Now, presumably, the self-driving car depends on perception systems that use some kind of image recognition algorithms. And if your image recognition systems are not even robust in the senses that I was talking about, there is no way that you could verify any kind of safety property, no matter what the formal model is. Yeah.
A was bad, then A plus B is also going to be bad.
Right.
But that's all. I mean, I
Yeah.
don't want to take up time there.
Sure.
I could just imagine that there are very simple constraints, like the car is not gonna decelerate from 100 miles per hour to 0, right? Or what could you pose to us, and verify simple constraints like that?
Yeah. So one example that actually drove a lot of the initial verification work is this paper called Reluplex that came out of Stanford a year back, where they were working with the FAA on. The FAA has defined some set of rules that they want like autonomous drones to satisfy, and there are things like, if you detect an intruder and the intruder is accelerating towards you in a certain direction, you don't want to recommend an action that forces the drone that turns closer towards. So there is these like sanity rules that can be defined purely as input-output properties of the neural network, which may not be sufficient to guarantee safety overall, but they're at least reasonable sanity checks that you can impose on a neural network. Question?
The adversarial model that you have in propagation and all that,
Yeah.
it seems very closer to things we do in game theory, where an adversary is putting an input and you have, like in controls, this has been a classical model.
Right.
Where adversary is adding its control, the controller is adding its control, the state is propagating.
Yeah.
And you find the worst case attack by the adversary
Uh-huh.
by formulating it as a zero-sum game.
Uh-huh.
So in your case, when you put the max over epsilon, blah, blah, blah,
Uh-huh.
and then you're essentially doing a minimization when you are training the neural network,
Yes.
and your weights are essentially the control variables.
Yes.
So is it like directly connected to?
It is a minimax problem, yes, and in that sense, it is a zero-sum game,
I see.
right? Yeah, but I don't know that. I don't obviously see any useful results we can relish from game theory, but if you think that there are, I'd be happy to talk to you offline.
Because these backpropagation algorithm is same as minimizing Hamiltonians in controls.
Uh-huh.
Exactly the same mathematically. And so there are lots of algorithms within controls and games, intersection of controls and games, where they do this open loop control computation and open loop attack computation
Right.
by using these backpropagation. And I think some of the tools from there can be borrowed to maybe prove something, or I don't know.
I think that would be great. Yeah, I'd be happy to talk to you offline about that. Yeah. Yes.
I think you mentioned that your results apply to only two-layered networks. I'm curious where this restriction comes from and how does the number of layers actually affect problems?
So it's the theoretical results that only apply to two-layer networks, right? The theoretical results about being able to do verification exactly. Being able to compute bounds we can do for an arbitrary number of layers. It's just proving that those bounds would be tight we can only do for special cases.
Okay, cool. And also, do you know how do the bounds degrade? Like, what is the law which speeds?
Right. So this is a very tricky question to answer. So what we found in our experiments is that if you train networks without having this verification as feedback, then you can quickly get to networks that are very difficult to verify, and the bounds kind of kind of explode as the number of layers grow or as the number of neurons grow. But if you do this idea of folding the verification back into the training, we are able to train rather deep networks that are still easy to verify, and the gap between the bounds is small. So it's the gap is not a simple function of the number of layers or the number of neurons. It actually depends fundamentally on properties of your network. Yeah.
I wonder if you can formalize this problem as I did in my talk, in the sense that you have a black box that gives you yes or no.
Yeah.
You have all the world, and you don't have time to check all the possible questions. And maybe you also know that you want to get yes on the one side of the world and no for the other side. Then it's kind of active learning problem when you raise the question that I need to verify the minimum number of questions to know how my space looks like. Does this make sense?
Yes, in principle it makes sense. I don't see an easy way to come up with a proof that says that if you verified these k points, then you know that you're safe everywhere else. But I'd be interested to talk to you offline about that. Yeah.
So the button is probably depend on the function, right? Like in my talk, of course, it depends on your exact network and what you assume about this, and then you can say if the function are this and this, then I think that this question will do something like this. That's what we expect to get. But then I think this can be, using active learning machinery, we can actually get good trade-off between number of questions and what you learn about the world under the assumption of the networks.
Right. Yeah.
Thank you.
Okay, let's then go to speaker again.